just as you can have operators over numbers like plus and times for addition and multiplication, there are some operators, crucial operators, that work over functions themselves, and that's what we'll look at here. So one of the most fundamental things we can do with functions is to compose them, to feed the output of one function into the input of another. And here we're seeing the composition, that's what it's called, operator in Haskell is denoted by a dot. And f dot g gives the composition of f and g. Now it's important, it's kind of crucial in this to know which way round the plumbing works. And the way it works is f dot g means f applied to g of x. So the way the functions are applied is the same as the order in the composition. So the first function to be applied is the one on the right of the dot. So f dot g of x is f applied to g of x. And you see that illustrated here. F dot g is the box, and inside the box you see the value going into g first, the output of that coming and being fed into the input of f, and then the overall output being c. So lots and lots of functions can be defined this way. So if you remember when we rotated pictures by applying flip v and then flip h. So we could say that rotate equals flip h dot flip v. You can define the function at the function level by combining the two functions flip h and flip v with the operator dot. Now what about the types involved? Here they're denoted A and B and C, and that helps us to see what the type of the operator dot will be. We have the first argument of dot is f, so that's the function that goes from B to C. The second argument of dot is g, and that's the first function to be applied. So that goes from A to B. So the output type of G has to be the same as the input type of F. And the whole thing takes an A, which is the input of G, to a C, which is the output of F. And that's because we pipe the output of G, which is of type B, into the input of F, which is also of type B. So this is a polymorphic operator. We don't know anything about the types are arbitrary, they're function types, but what we do know is that the output of the first function, namely g, must be the same as the input of the second function to be applied, namely f. So that, remember, dot here means function composition. So it's quite different. It's a different use from in many object-oriented languages, for example. Now, how does using that operator interact with something like applying a function? So we can create the function not dot not, which is not over booleans composed with itself. What happens if we apply that not dot not to false, and we write it like this? You can try it if you want. Pause the video here, and I'm going to say, what does not dot not apply to false give us? And the answer is we get a type error. It says not is applied to too many arguments in the second argument of dot. So it looks like it's being read as not dot, not false. Because if you remember, all the time, so we get the same, all the time in Haskell, that function application binds more tightly than anything else. So if we want to compose not with itself and apply it to false, we have to parenthesize it. And then we get the answer that we would expect. That is not Not applied to false gives true, and then not applied to true gives us false back. And let's just define a couple of functions. F of x equal x plus 2, and let g of x, g of y equal x times 3, y times 3. So we've got those two definitions. Then what happens if we apply g dot f to 3, 2? What would we expect would happen there? Which thing gets applied first? F gets applied first, so we'd expect it to 2 gets turned to 4, and then the whole thing gets multiplied by 3, so we would expect to get the answer 12. Whereas if we do f dot g applied to 2, we would expect to get 3 times 2, which is 6, plus 2 is 8. And that's indeed what we get. So you can see here that function composition, the order in which you compose the functions, is obviously significant, because the thing on the right is applied first, followed by the thing on the left. So we've tried that, and as we can see, because juxtaposition application binds tighter than anything else, including the dot operator. Now we can also define an operator for ourselves, arrow dot arrow, which is like dot but has the first function on the left. So g arrow dot arrow f is the same as f dot g. So it's g then f. And so if we're thinking of doing rotate, and we want to first flip v and then flip h, we can write that rotate as flip v greater than dot greater than flip h. First flip v, then flip h, and we're using those symbols greater than here to indicate the direction in which the composition goes, because normally the function on the right is applied first, but here we're applying the function on the left first. Okay, so those are two ways of wiring functions together, feeding the output of one into the input of another. The other operator in Haskell that gets used more than you might expect is the dollar operator. It's the infix application operator, so that f $a is just f applied to a. Now you might think, why on earth would we ever bother to write a dollar when it's just f applied to a in the first place? Now there are two reasons for doing this. The first is a matter of making things a bit easier to read, or having to type a few fewer symbols. So instead of writing brackets as we have in flip v applied to brackets flip h, brackets rotate pick, we can use dollar instead, and dollar, we can say flip v dollar, apply to everything on the right hand side, flip h dollar. And so here dollar is right associative, and it is it's meaning that we have to write fewer parentheses. So it's a stylistic thing that some Hasslers really like. But in a way, that's just about syntax. It's also useful because we might actually want to think of dollar as being a value in its own right. So here's an example where I have applied the function dollar. I've used it in a zip with, and what that means is that for each corresponding pair, dollar is applied to the two arguments. So dollar of sum and 1, 2 will give us the result 3. Dollar applied to product and 3, 4 will give us the result 12. And indeed, we could try that out interactively. So we could zip with dollar, and what we were saying, sum product and the list 1, 2 and 3, 4. So we would expect that to give us the list 3 and 12. And indeed it does. So, because what that did was it applied dollar to sum and 1, 2, so that is summer gets applied to 1, 2. It applies dollar to product and 3, 4, so product gets applied to 3, 4. So we've seen two crucial operators for functions here. We've seen dot that composes two functions into a single function. We've seen dollar that is the operator that applies a function to an argument, and it's used sometimes to make syntax, to make expressions easier to read, and it's also used as an operator, as a function in its own right, as we saw in the example here.